All right, let's go. All right. Two quick public service announcements. Second quiz is tonight, due at midnight, so don't forget to do that. Do it early, get a little extra time between your first and second attempts. Do it again and get 100. Okay?
Is it due at midnight or due at 5?
Oh, it shouldn't be due at 5. It might be, though. It's supposed to be due at midnight. You got it messed up on here?
Yeah, it was due at 5 when I took it last night.
Oh, man.
No.
We all have the same classes, I guess. Mine looks right. September 21st, 11:59 p.m. So your Physics 202 might be messed up. But either way, quiz 2 tonight. It looks like it's right. And then also, we've got discussion videos online in the event that you get COVID and you can't come here, or you do miss a discussion, but you still want to see somebody talk through the problems instead of just seeing the solutions. Like, we're going to post the solutions, but if you want someone to work through them, one of our TAs is screen capturing what they're writing down. So discussion videos, if my mouse worked, you could click on that, and that'll take you to a YouTube channel that he's posting them all at. So in the event that you miss, don't feel like you're totally left in the dark. Come here and check that out. No guarantee that he's going to upload every day right away, but hopefully they'll be up there after class. So one more thing to lean on, okay? All right. So today, we're going to talk through two sections. We're going to talk through a time derivative of a vector. So we'll do like a little math lesson that we'll use as a tool for the following section. So this is just a little thing to get out of the way for us. So to intro this, the first day of class, we looked at velocity and acceleration in a Cartesian coordinate system. So Cartesian coordinate system, x and y, I and j. We've essentially bolted this thing down to the paper. It's not moving anywhere. It's not rotating anywhere. It's fixed in space. So if we had some point that we're trying to get to, and we had a position vector, maybe this point kind of wiggles along in time, so our position changes as a function of time. Our r vector had x components in the I direction, y components in the j direction. So I guess if I did this and this would be my rx, and this would be my ry, right? All right. To get from position to velocity to acceleration, we took some time derivatives. We said velocity is our time derivative of position. One thing that we kind of swept under the rug is that really I've got a product here of a magnitude and a position vector, or a unit vector I. So when I'm looking at our derivative r here, I've really got r dot of x times I, and then the product rule, I can take the derivative of the second piece times the first, plus rx times I dot, the time derivative of my I vector. Same thing for my y components. R dot y in the j direction plus ry in the j dot direction. Hey, I've taken this Cartesian coordinate system, and like I said, I've kind of bolted it into position. It's not doing anything. It's not rotating or changing. So my unit vectors are just going to be the time derivatives of my unit vectors. They're not changing. They're going to go to 0. So my velocity was just r dot x in the I direction plus r dot y in the j direction. Acceleration, just add an extra dot. One more time derivative. Same story, though. And now comes the tricky part. So, Cartesian coordinate system, sometimes handy. What we're going to look at for the next 2 days is polar coordinates and normal tangential coordinate system. So, if our particle was traveling a straight line, maybe Cartesian would be the easiest way to describe it. But had we been going in like a circular path, or even my little squiggly path that I've drawn here, we can get more information about acceleration and velocity, well, maybe more easily, if we use a different coordinate system. So polar and normal tangential. So today, we'll talk about polar coordinates, but in order to talk about polar coordinates, we've got to kind of get into this idea of, what's the time derivative of that vector? So for this case, because our unit vectors were locked in position, time derivative was 0. It's not always going to be the case, though, once we start looking at polar and NT systems. They're going to change orientation, and we got to be able to track that. So, if we do the same idea again, I've got my A vector. I want to look at the derivative of this A vector. So, the time derivative of A, this is going to be d by dt of my A vector, which I can write as a magnitude and a direction. What's its direction? It's pointing towards A in its same path. So, if I take the derivative of this using the product rule, I get A dot u hat of A plus the derivative of the second piece times the first. A times the time derivative of our unit vector A. This is what we try to figure out today. This first piece maybe doesn't hurt our brains too much. Hey, I'm still pointing in the same direction as A. So maybe this is my original A vector. I'm still pointing in that same direction, but A is changing its magnitude. So maybe it got a little shorter. Maybe it got longer. But this is the component. I think of this as the magnitude. How much is it changing its length? This direction. Maybe it's no longer pointed over here. Now maybe it's pointed over this way. And it's swung over. So magnitude, I think we can get pretty easily. The direction change is a bit sneakier. So that's what this slide is actually showing, just this little redrawing of what I've got here. This first piece, magnitude. Second piece, the mystery part, still direction. Okay. All of that old news. Let's figure this out. What does our unit vector time derivative look like? So say we've got some point that we're tracking, our point A. I'm actually going to make this a unit vector too. So if this was like magnitude 1. I can write my unit vector for the a direction in terms of this angle theta that I just tried to scribble in there. So it's going to be the cosine of theta in the x direction and the sine in the y direction. So this is cos theta I plus sine theta j. All right. We're interested in what the time derivative of this guy looks like. So let's do that. Let's take a time derivative. All right. My derivative of cosine of theta with respect to time. Derivative of cosine is minus sine, so minus sine theta. But it's a time derivative, so I got to take the derivative of theta with respect to time multiplied by theta dot in the I direction. I could do the second part of that, cosine theta times the time derivative of the I unit vector, but that's staying still. So we know that part's going to fall out. So now for the second piece, for the j component, derivative of sine is cosine, cos theta, derivative of theta with respect to time, theta dot. So what does this look like? I can pull a theta dot out front. So minus sine theta I plus cos theta j. I promise you we're getting somewhere. This piece, we could draw that in if we wanted. So I got minus sine theta in the I direction. Hey, that's my sine theta component. But now it's in the minus I. So I take that piece and I kind of put it over here. That's my minus sine theta. My j component, cosine theta. That's this piece, but now it's in the j. So that's over here. This guy points in this direction, which is exactly perpendicular to our original u vector, or u sub a. So if we think of like, hey, if this is angle theta, this side over here is also angle theta if it's perpendicular, because I've just taken this coordinate system, I just rotated them both by theta, right? So if I look at that, this is my sine theta leg, and that's in the x. This is my cosine theta leg, and that's in the y direction. So if you didn't really believe that they were perpendicular, you always could have done a dot product, where you could have just looked at u hat of a dotted with this guy, and you'd find that dot product is 0. So that just tells us that this is perpendicular to our original unit vector. Okay, we're going to take this. We're going to hide that in our back pocket for a second. I'm not going to do a formal proof here, but I'm going to just like show you a shortcut for getting us to this point. This is the derivative of that vector. I'm going to tell you that it looks like this. The angular velocity of our coordinate system, omega a, crossed with our original unit vector. So we'll show that this is actually that. So our angular velocity of a, this is my coordinate system, and it's rotating at some rate. Here's my position theta. We measure positive counterclockwise in a traditional right-handed coordinate system. So the rate at which it's moving in that theta direction, or in that rotation direction, that's going to be my angular rotation for this coordinate system. So if I think of this as a new coordinate system, how fast is that rotating? So the time rate of change of theta is omega. Omega is our angular velocity, so we call that theta dot. And that, for everything we do in this class, we're dealing with things in a plane, 2D. So x, y, our z direction is going to be out of the board. So it's rotating in the z. So it's theta dot in the k direction, crossed with our unit vector for a, which we wrote out up top. So cos theta in the I, sine theta in the j. You've got to do a cross product. How I do cross products for simple things when I only have one component to multiply. Now look at my first piece. Theta in the k direction. It's pointing up this way. I cross that with the I direction. So I start my fingers in k. I curl them towards I in the direction my thumb is pointing, back in the z, or sorry, the j. That's what I'm going to get. So I get k. I cross it towards I. And I get theta dot cos theta in the j direction for this first term of the cross product. Now, my second term, I've got theta in the k direction, crossed with sine theta in the j direction. So now I'm rotating it this way. So I start my fingers pointing towards k. I rotate them towards j. And my thumb is now in the negative x direction. So I've got minus theta dot times sine theta j. Sorry, I. Because this is going to end up pointing in the minus I direction. Rearrange this guy. Omega A cross u hat of A. Hey, it's exactly what we wanted to see. This is the time rate of change of that unit vector, which, if I swap things around here, I get theta dot sine theta I, but with a negative out front, plus cos theta j. So this part, we're just using to show that our unit vector's time derivative is actually equal to omega cross the original unit vector. This is the piece we need. This was just our way of getting there. So the story we tell to show you that, hey, the time derivative of that unit vector, I can make sense of that if I put it in a Cartesian system. But really, the time rate of change of that unit vector is just omega, our angular velocity of that vector, crossed with the original unit vector. So that's the piece we need for today. All right, back to the beginning then. When we talked about our derivative of a vector, the whole vector itself. We said we had two pieces. A dot times its unit vector plus A times u hat dot of A, the time derivative of the unit vector. This we have an expression for now, so we can substitute in for that. A dot u hat A plus A times omega cross the original unit vector. Again, getting closer to being useful. A is just the magnitude. Its direction is u hat A. So if I took this guy and I snuck it in over here, that's just my original A vector. So all that hard work, the time derivative of a vector its magnitude change in its original direction, plus a rotation crossed with the original vector itself. Change in magnitude, change in direction. A vector, we got to chase both of these pieces. And we'll use that to describe velocity and acceleration in polar coordinates. There's one more slide. Okay, this gets a little messy. I'm going to do it quickly because it's just math. If I need to take a second derivative, well, let's just cruise through this. A second derivative of A. My first part, I got to use the product rule because I got two pieces. I got the magnitude and the direction. So the first piece, derivative of that times u hat of A, plus the derivative of my unit vector times A dot. We just spent a bunch of time figuring out what this was. This was just omega cross A. Or actually, omega cross u hat of A, because it's the unit vector. Sorry. And now I have to take the derivative of my second piece. Derivative of my first piece, omega dot of A, crossed with my A vector, plus omega of A crossed with A dot. Hey, A dot. It's this whole thing. Bringing that in. So you're looking at this, and it just gets messy. I've got my first term, a second term, a third term, and then my fourth term, I've got a bunch more to bring in there. So you could crank through, add this in there, distribute everything out, but what you're going to end up with is what's on the screen. So I'm not going to bother rewriting it. Second derivative of a vector. Oh, no. Several different components. When you get to advanced dynamics, you spend a little more time when you're in 3D talking about all these different components. But, hey, our first component, A double dot in the A direction. This is the magnitude of our acceleration change in the A direction, so pointing along the original vector. This guy, we're going to have two different components that add up to 2 omega cross A dot. That's what we call our Coriolis effect. This one, our third component, that's here. Omega dot, remember that omega is theta dot, so omega dot is theta double dot. This is our angular acceleration crossed with our initial A vector. So this is like acceleration in a direction perpendicular to our original A vector. Then what we'll get at the end, a double cross product, omega cross A. This term, big term, double cross product, it seems like a pain in the butt. And when you do 3D, it is. But in 2 dimensions, which we'll show for polar coordinates, it actually simplifies quite a bit. So it's not that hard to deal with in a 2D sense. So that we'll do in a second. All right. Math lesson behind us. We just need to put that to use now. We want to use polar coordinates. Polar coordinates, super useful if we're going on a curvy path. Really, really useful if we're traveling on a circular path. We want to be able to describe velocity and acceleration for these. So how do we write our r vector in polar coordinates? Our r vector is just some magnitude r in the r direction. Okay, wherever our point is, that's the direction u hat r. So from some original location pointing through our point, that's our r direction. So as this point moves in time, our r direction also will move in time. If we want to figure out our velocity, now we have to use those derivatives we just played with. Our velocity is the time derivative of our position. So, time derivative of position. R dot u hat r plus r times u hat r dot, the time rate of change of our r vector. All right, let's see what we know. This is the thing that we just used a derivative of a vector to figure out. So the time derivative of my r vector, omega r cross the r unit vector. That's the definition we just worked on. So our angular velocity, this is going to be our theta dot. Again in the k direction, because that's out of the plane, crossed with u hat r. So for a polar coordinate system, I've got an r direction, a theta direction, and a k, or z direction. So for this cross product, I start in k, I curl towards r, and I'm pointing in my theta direction. So this derivative becomes theta dot in the u hat theta direction. So that's what this guy is. So my velocity, r dot u hat r plus r theta dot u hat theta. All right. So what do we need to know? We need to know our r direction. I've got some origin. From the origin to the point I care about, draw a line, and that's going to be r. The theta direction is going to be 90 degrees from that, positive counterclockwise. So 90 degrees positive counterclockwise, u hat theta. So if this little particle was kind of moving along in time and then ended up here, I need to draw a new r and theta system. So my r would go from my origin through this guy. My theta direction, 90 degrees to that, positive counterclockwise direction. So this is u hat theta. But you can see that they're no longer aligned. So they're changing direction, and that's the interesting part that we have to keep track of. So my velocity's got two components. It's got a component in r, the original direction, and that's r dot. Then it's also got this rotational component, r times theta dot. How is our angle of this coordinate system changing? So two pieces that we need to keep track of. All right, that's velocity. Let's go one more. We're going to do acceleration. So acceleration in polar, it's the time derivative of the velocity that we just wrote. dv dt. So let's crank through it. My first term, product rule. My r dot goes in r double dot times u hat r plus r dot times u hat dot of r, which we just calculated as theta dot times u theta. So this guy, theta dot u hat theta. Our second piece, maybe I'll bundle them like this for the product rule, where I'll do the first piece and then I'll do the second. So derivative of my first piece, r dot times my second piece, theta dot u hat theta, plus derivative of my second times my first, plus r times a nested product rule. So I got to go one more time. My theta dot goes to theta double dot plus theta dot times the derivative of that, theta dot times the derivative of my theta direction. This one we didn't figure out yet, but we have a rule for that. The time derivative of theta dot is omega. In the k direction, I'm going to actually call that theta dot so it lines up better with our other things. Theta dot in the k crossed with the original vector, u hat theta. Draw my little coordinate system, because it's the only way my brain works. U hat r, u hat theta, in k. This is k, I start in k. Cross towards theta, so I point up, curl towards theta. Thumb is pointing in the minus r direction. So this becomes minus theta dot u hat r. Okay. We're left with a bunch of stuff. Clean it up to make it a little more digestible. I've got an r component. We've got a theta component, another theta component, a third theta component, and this one, if I look down here, is actually an r component. So let me group this into the r's and thetas. So I'm going to have stuff in the r direction plus more stuff in the theta direction. So for my r direction, I get the first piece, r double dot, and then I've got this guy. So an r times theta dot times minus theta dot. So that's a minus r theta dot squared for this one. For the theta direction, I've got an r dot theta dot and another one, r dot theta dot. So I've got two r dot theta dots plus an r theta double dot. This is my acceleration in polar coordinates. The first piece, that's my acceleration in the radial direction. The second piece, that's the acceleration perpendicular to that in the theta direction. Quickly, when you're writing through these and you think, well, how do I know that I'm even like on the right track? Hey, acceleration, you think of like units. meters per second squared. So I've got like 2 time derivatives. So r double dot, derivative with respect to time again. I got a per second squared. Here, my rotation, radians per second. So I got squared that. I get meters per second squared. And here, I got 2 r dot, meters per second, theta, radians per second. So that means meters per second squared. And then here, meters for r, theta, radians per second squared for double dot. So everything here, if I was using SI units, would be meters per second squared. Units all seem to align and make sense. So this is our acceleration. We got multiple components for what's happening in that radial direction, multiple components contributing to what's happening in that tangential direction. So a lot to keep track of. Phew. All right. We're going to use this equation now. We'll use the one for velocity, r dot in the r direction, plus r theta dot in the theta direction. So we'll use our velocity and acceleration equations to solve some problems where particles are moving in funny directions. They're circular paths or following some bizarre spiral, and it's given as a function of theta. All right, this problem. We got the motion of our particle B. It has to travel in this spiral shape. It's controlled by this groove. But we've got a rotating link. That's our vertical component here, OA. This thing's going to rotate at some angular velocity theta. And that's a constant angular velocity. So I know that theta dot is 6 radians per second, constant, so theta double dot is 0. We want to determine the magnitude of the velocity and acceleration. So we want to find the magnitude of velocity and the magnitude of acceleration at theta is equal to pi over 2 radians. But the last piece of information we need is our path. Our path is defined as r is equal to 40 times theta, and that's in millimeters. So as we move our angle gets larger and larger and larger, we spiral out from the center. All right. First, we want to find magnitudes. Our velocity and accelerations each have multiple components. So the magnitude of a vector with 2 components, vr squared plus v theta squared square root. Same thing for acceleration. ar squared plus a theta squared square root. Let's use our definition for polar coordinates to figure out how to find our velocity components and our acceleration components. So velocity first. Velocity is equal to r dot u hat r plus r theta dot u hat theta. Okay? I'm trying to figure out what these guys are. R dot is my time derivative of the r vector. I'm trying to figure it out at a position that we know. Theta is pi over 2. So in order to get r dot, I got to say what I know about r and take its time derivative. So r dot is the time derivative of r, which is 40 theta. So d by dt of 40 theta. 40 stays there. The time derivative of theta, theta dot. So my r dot, 40 theta dot, and I know theta dot, 6 radians per second. So we got 40 times 6 radians per second, and my 40 was in millimeters. So that piece is done. So this is actually my VR component. It's just r dot in the r direction, and that is 6 times 4, 24, 240 millimeters per second. 1/4 of the way there. The theta direction. V theta is r theta dot. Hey, theta dot we're given in the problem statement. 6 radians per second. R we're given as 40 theta. And I want to find that theta equals 2 pi. So my r is 40 times theta, which is pi over 2, times theta dot, which is 6. So just plugging in for what I know. I've been given r as a function of theta, and I want to know everything that's happening at a specific value of theta. When I've gotten to theta is equal to pi over 2, which would be exactly this, the position shown, 90 degrees. So 20 pi times 6, 120 pi. Find my velocity, square one, add it to the square of the other, and square root. So my magnitude of V is the square root of VR squared plus V theta squared. 240 squared plus 120 pi squared. So if I didn't screw that up, 447 millimeters per second. All we've done, though, we've just taken our definition for polar velocity, and we've substituted in, worked our way methodically through these values to figure out what our magnitude of velocity is. One more time for acceleration. Our acceleration in polar is a little gnarlier, though. R double dot minus R theta dot squared. In the R direction, R theta double dot plus 2 R dot theta dot in the theta. We got to go and we got to chase these out. The only little bonus here is that our theta double dot term, our angular acceleration of this rod, was 0 because we had a constant angular velocity. It's like a clock second hand. It's always rotating at the same speed. It's not speeding up or slowing down. So this term mercifully falls away for this problem. All right, so for AR, R double dot, I take the second derivative of my R vector. Well, my R vector was, if I just do this instead, R double dot is the time derivative of R dot, which we previously had as 40 times theta dot. So this is 40 times theta double dot. And luckily, theta double dot for this problem is 0. So R dot is also 0, or R double dot also falls away. One piece is a little bit easier. So that leaves me with our acceleration in the radial direction as minus R theta dot squared. Our r, we actually solved for that because we've got r as 40 times theta. So we've got minus 40 times theta, which is pi over 2, times theta dot squared. Theta dot, 6. So with the negative value, I've got minus 2,261.9 millimeters per second squared. One component of my acceleration. I need to still chase after the other one. So a theta, talked about the first term being 0 plus 2 times r dot. If I jump back, I've got r dot. It's 40 times theta dot, which we've previously written as 6 radians per second, times theta dot again, which is again 6 radians per second. So this, 2,880 millimeters per second squared. So my magnitude of acceleration, AR squared plus A theta squared, square rooted. All right. 3,662 millimeters per second squared. A whole lot of writing real fast, but the actual application of what we've done is pretty simple. We started with our equation for velocity in polar, substituted in what we know. We started with our equation for acceleration in polar coordinates and substituted in what we know. So, a whole lot of work, but if you just go slowly, you think, hey, read the problem statement. We know what theta dot was constant, so we know theta double dot. I've got a value for r. I need to take some time derivatives. Okay, I've got one more problem that we're not going to do, obviously. I'll post the solution to Canvas so you can see that.